Okay. Hello, everybody. We've got, DC-MHS is made up of a whole bunch of people working to make this happen. Already this morning, you've seen 4 or 5 different people from DC-MHS. Here today, we've got a panel of others that are contributing to the effort. It is a good makeup of different companies that are contributing, and we're going to go through. This is a panel. It is interactive, so at any point, just raise your hand, come to the mic, ask a question. However, each of the panelists here have some material that they want to go through to help get the conversation going. So we're going to go ahead and lead off with Brian here. And well, actually, let's go a quick introduction through everybody. Matt, do you want to start?
Sure. Hello?
All right. Okay. Here you go.
Hello, my name is Matt Bowman, a hardware engineer at Meta.
Andy Junkins, principal engineer at AMD.
Corey Hartman, and concept architecture at Dell.
Mike Gregoire, also on the concept architecture team at Dell.
And Brian Aspnes, principal engineer at Intel. Okay, so my name is Brian Aspens, as I said, so I'm one of the project leads with Sean. I just wanted to go through the activities and timeline since the last Global Summit. So as you can see here, back in January, we had the release of our 1.0 specs around the end of last year. This year, you can see the timeline of the various spec releases, and then a summary table of the latest specifications. So you can find this available in our public calls. But what I'm trying to convey on this timeline is our dedication to continuing the specs. So there's several specs that we're showing. For example, the Dino, the PESTI, the XIO. These are all specs that we're planning on doing maintenance releases on. So even though they're at 1.0, you're seeing the 1.01s, the 1.02s, et cetera. What we're doing there is, as we get feedback from the community or we have some additional new feature, we will continue to provide those updates this year. So be on the lookout for those. We do have some new specifications that we'll talk about today. 2 of them are the SDNO and the shared infrastructure. Those are both at 0.5. So those are 2 topics that we'll cover today to give you more information about these specs. Next slide. So this group specifically is the HPM work stream, and we have 3 specifications that we are currently working on. So the first is our full width specification. You saw from AMD the full width board. That's the full 19-inch chassis. And as you can see here, we released the revision 1, the 1.01 around June of this year. And we plan to continue maintenance releases on those for the rest of this year. And then we also have our M-DNO specification that we call Rev 1.0 version 1. And you can see the same thing there. So around July, for our Dino specification, there's additional updates. I think for example, on the 1.01, one of the updates was making the OCP NIC as recommended but optional. So that's an example of a change in the Dino spec. No plans to obsolete that spec either. The one that we'll be talking about today is our new specification called MS-DNO. It stands for Scalable Dino. And so scalability and the ability to change the depth is one of the big features of this spec. The second big difference versus our M-DNO spec is the addition of HPMs for 21-inch chassis, our OpenRack V3. So this is now part of our MS-DNO spec that my panelists will talk to. The other thing I want to touch on is right around June timeframe, we released a spec called M-DNO type 5 to 7. So at that point in time, we weren't exactly sure if we were going to combine the Dino and this spec. And so we didn't really give it a name. It was called directional. We want to just say that has recently been replaced by the MS-DNO spec that's now available on our wiki at a 0.5 level. So don't get confused by the naming change there, but that is just an early, we call it like a 0.3 version of our MS-DNO spec, basically, with larger HPM support. Go ahead.
Okay, so these next few slides, we kind of want to talk through, introduce S-Dino, talk about what's different and what's similar. As you can probably tell, if it's called Scalable Dino, it has a lot in common with DNO, but there's enough difference that we decided ultimately to do a separate specification for it. So probably the biggest change is that we're no longer using what we call board types. So if you go out on the show floor, you can see the FLW boards, Dino boards. They'll be called type 1, type 2. The original Dino had type 2 as this base form factor, and there was a longer one called type 3, a wider one called type 4. As we started to think about how do we address this much larger scope with 19-inch and 21-inch, we decided to take a little bit of a different approach so that we wouldn't have a million different board types. So instead, we're defining what we call HPM classes. There's 4 of them. Each class has a consistent width and feature set, so that might be number of risers, how many power placements there are, but the length is allowed to vary within a minimum and maximum. And we think of this somewhat like PCI chem card. So we talk about what we call common chassis intervals. These are common chassis envelopes that we believe HPMs will want to fit within, and if you don't, you're potentially going to size yourself out of some of the marketplace. But much like a full-length chem slot in a server, if someone wants to make a board that's 20 millimeters shorter for some reason, save money on a panel size or what have you, it will still fit in my full-length slot. In a similar way, if someone wants to make a 535 millimeter HPM, it will fit in a 555 chassis. So on the next slide, we'll start talking a little bit about the different classes. So as we alluded, this is trying to span 19 and 21 inch. So we have a half width for both and a full width for both. So in the upper left there, we start with what we call class A. This is the 19-inch half width. This looks a lot like a Dino Type 2 in this drawing, and it is almost identical to what you'd see out on the floor in the various Dino 2 boards. There's some slight differences that we'll get into in a minute here, but otherwise consistent, 2 riser slots, optimized for smaller one-socket designs. As we step up to Class B, that's our 21-inch OpenRack V3 optimized half width. This, of course, also can be placed in 19-inch infrastructure. It's wider, right, so you get a 3rd riser slot, but probably more importantly is there's just more room for all of the things that we've been talking about for days here at the show, more power, more memory, et cetera, keep outs to enable liquid, et cetera. We step up from there to Class C, which is a 19-inch full width. You might say, hey, there's already a full width spec, why do we need this? This is a very different system layout because it's a rectangular Dino style board that doesn't have power supplies plugging directly into the HPM, right? There's a bus bar, there's a PDB, power is being cabled into the board. So you end up with a pretty different feature set between a Class C and an FLW. The 0.5 spec, we only have a little bit of information about Class C, but more will be coming in the 0.7 release. And finally, Class D, this is a full-wide 21-inch optimized for OpenRack V3. This is probably the most unique because it's the most constrained environment. The half-width boards could be in 19-inch or 21-inch, so there's some variety in where they'll be placed, but this Class D is a really full 21-inch wide, 512 millimeter board optimized for OpenRack. So with that, I'll pass it over to Corey to talk a little more about the details.
So on the HPM scalability, The key thing about this approach that Mike described is the ability to vary the different lengths. So there is a set of floating features and a set of fixed features. So the fixed features are generally at your chassis bulkhead, your wall, and that allows all the different form factors to be compatible. And then the floating features are defined, essentially a formula that allows whatever your board design length or your chassis design target, it gives you deterministic rules of that ensures compatibility between a chassis designed on day one and some HPM designed in the future. Oops. So the zone two, the zone two approach, we had a specific problem there, and we had to come up with a solution to enable the scalability. Zone two refers to the bottom side keep out zones. These are in place to interface to fixed chassis features, such as some sheet metal forms or some press pins, but that has been fundamental to some of the M-HPM HPM approaches that allow common chassis to support multiple HPM types and future HPMs. So two big problems that we had to tackle. One of them was some of the near-term experiences that the previous group talked about in terms of routing and placement. The KOZ approaches that we had in the DNO2 approach, we kind of saw the need to relieve some congestion and some relief in some of the placement there. So the KOZs have been kind of moved as far to the corners as possible to open up as much flexibility in kind of that core compute area. The other problem was when you overlay these goals of having multiple board sizes all within common chassis, when you overlay the potential keep-out zones and mechanical constraints, it was really over-constraining the larger board form factors and negating the placement options and that's one would use a larger HPM for. So the solution was to come up with this formula with some fixed and floating KOZs. So the fixed KOZs are at the kind of on the half point to the near side. So formulas in the spec for exactly where those go. And then the floating KOZs are attached to that far edge. So depending on your target chassis design length or your target board length, you have this approach to attach those KOZs at that area, and that ensures that whatever your target chassis design length, for example, a 400 millimeter chassis, by following these rules, any HPM that's equal to or less than that target length will be compatible. So even if you had, say, a 300 millimeter board to put in that 400 millimeter chassis, through the use of the board pan, you can reach those floating KOZ locations at the far side. And so any board in the future that's, if it's targeted 400, it will be compatible by following the formulas that we put forth here.
So let me speak a little bit to the compatibility story because it can be a little confusing. So with these four classes, again, divided as 21-inch optimized, 19-inch optimized, the intent is that you could design a chassis to a full width support. So if we take class D, which is the 21-inch full wide, and you can enable then the ability to have two class Bs in there or two class As in that same chassis. Right, that's a design choice you can make, and all those keep outs that Corey just described and all the connector placement is compatible. Similarly, that's the same intent then for Class C's relationship to Class A. So you could have a Class C chassis that could support two Class A's or a single Class B. And so the overlay example on the left side of this chart, the 21-inch, is showing how this lays out physically, right? So the Class D being the large rectangle here. The length chosen here are kind of arbitrary for this example, but you can see here what you're doing is you're aligning the origin of the Class A's and Class B's on the left side of this diagram. And if you want to have two hosts in that tray, you could do that on a very specific pitch, which is 262 millimeters. And that's an important note because if you vary from that, you won't have that compatibility. And of course, this is a case where if you want to enable two hosts in one tray. Now, of course, if you're doing a true half-wide like a multi-node, you could design, for example, maybe a half-wide tray for 21 inch, so that'd be your Class B, you could still put a Class A in that tray. Okay, so you still have that compatibility as well. The bottom right side of this chart has some examples to kind of illustrate what that might look like. You know, ultimately, as a system designer, you're going to have some depth limitation on your HPM that you're going to choose and design around, and that's going to define your, you know, what length HPM, maximum length HPM can go into that system. Anything shorter than that length should be compatible, right? So if you design your system to 335, you should be able to put a 325, a 305 HPM in there. Okay, that should be compatible. The HPM tray is an important element, though. It's used as kind of the hardware abstraction layer to give you that compatibility between different HPMs and your chassis. You don't have to use the HPM tray. You certainly could elect to directly mount your board to your chassis, but you're gonna kind of create compatibility challenges then. You'd have to have different chassis part numbers, perhaps. Okay. The next slide, just again highlighting Paul in the previous presentation went through what AMD has done so far. So we have the 2-socket SP5 on the floor. You can see in the full wide Type 1, and we've got this booted up now, and this is our first HPM. But the real message here is that, you know, we're just starting down the journey as well, but we plan more HPMs for our reference boards in the future, and, you know, AMD is fully committed to the DC-MHS ecosystem.
Okay, so Dirk showed you our Dino system on the right. On the left is our Intel's full width system. What Mike is holding up here is what Zane Ball showed in his keynote, which is a system from Quanta. But the idea behind this is that, you know, you can get a system from one of your CPU providers like Intel. We produce the entire chassis, which includes the PESTI, the PIC, the CRPS, the XIO, and all the firmware associated with that. So what we're showing you here is our Deer Creek system, which is our full width system. This board here would go into that system, whether it's Intel or Quanta, it's the same chassis. The one on the right is our Garden City system. That's our M-DNO Type 2. And so the idea behind this is that Intel will be, you know, producing systems on these form factors, and, you know, our goal is to easily enable the industry to consume and co-validate with us.
Hello. So I'm happy to show up on the slides here today. Meta is designing in support for SDino in our next generation chassis. In particular, this is called Yosemite V4. It's funny because I see Kieran in the audience, and he's giving a presentation on it later this afternoon, so consider this more of a teaser. You can see an example on the left side where it's the DNO board in one of our little chassis trays. And what I also wanted to touch on is why Meta is interested in the whole MHS, you know, what gets us excited about it. In particular, we always go through and have a make versus build versus buy decision as we're going through and designing in and getting stuff into our data center. What this lets us do is quickly evaluate and enable new technology. Historically, we've designed a lot of our own hardware because we had somewhat unique use cases. And as we've been participating in these work streams, we've been trying to bring it and align it, and both the work streams and ourselves, to get us in a place where we can use this. The accelerate time to production and the flexible configurations, particularly in like the AI ML world, is very exciting because you have instances where things come out in academia and in say like a 6-month cadence, there's this brand new algorithm that everyone would want to implement, and it would be very difficult or impossible to do brand new fresh hardware in 6 months. So having that queued up and have some readily available parts that you can grab, integrate, and get your stuff going, it gets us very excited and interested.
All right, so let's open up for questions for the panel here. If anybody has any questions or comments, please step up to the mic. If not, I'll give some questions here to the panel, and and see what they want to say about it. So first off, DC-MHS specs, they call out quite a few different requirements. There's a lot of features that one may look at and say, well, that's not exactly what I want. Is there something else that I want? Mike, what are your thoughts on that? Can I change stuff?
Yeah, so a common question, as Sean's bringing up, is, hey, I look at the compliance table and it seems somewhat arbitrary. Some things are required, some are optional. So a big model we have in our mind when we think about our compliance table and what it should mean to be compliant is, Brian designs an HPM and he doesn't call Dell and tell us anything about it. And we design a chassis. We're not talking to Brian. We want to minimize the impact of trying to take that HPM and put it into our system. There's a lot of folks who are building a DC-MHS board for a particular customer. Hey, you guys require the riser holes even if I don't implement the riser. Why is that? I don't need that hole. And it's because if a chassis or system vendor designs that system without knowing exactly who they're going to buy an HPM from, maybe it's 2 years down the line, we want all the mechanical features that would impact, reuse of subsystems and things to be in place. It may seem arbitrary at times, but that's really the litmus test for us is if I go to put an HPM into my system, I wasn't planning on the day I designed the system, is it going to be a huge effort? Or is it going to be relatively straightforward? Maybe some cables have to move, fine, but I don't want to have to retool a chassis base. So.
Yeah, and I just want to echo what Mike says. I think people are very used to designing their HPM for their chassis, right? And what DC-MHS is trying to do is say, you can do that for one system, but if you're interested in more than one system, you don't have to design all those from the grounds up. And I use this Quanta board as an example. It will plug directly into our Deer Creek chassis, and you can call up your system providers like Jabil, showing in the Experience Center where it just automatically plugs in, and you can test these in your labs without having to do the whole design yourself. I think Meta was echoing similar thoughts. So we do encourage you to try to be compliant for the compliant features that we call out in the specs.
Thank you, Mike. Thank you, Brian. So in the new spec, the Scalable Dino, scalable means choice. Choice can also mean incompatibility. I don't know, Corey, is that going to affect compatibility going forward? What are your thoughts?
Yeah, the goal was that, as Brian was mentioning and Mike were alluding to, is that interoperability was our top priority. So in the Scalable Dino spec, we had a much broader array of chassis environments that we're trying to fit into. So the team put a lot of work into coming up with rules and deterministic choices, right, to ensure that you could design or you could pick a particular HPM design target for cost reasons, for panelization reasons, for certain density options, and that you had enough rules in place to ensure that compatibility. So we certainly encourage everyone to take a look at the 0.5 specs that we put out and give us feedback on those items. But we feel like we have put the right rules and formulas in place that ensure interoperability, while meanwhile providing a scalable framework that you can accomplish a wide range of both 19-inch and 21-inch chassis design goals.
All right, thank you, Corey. And just a reminder, everybody, we do have an open mic right now. If anybody has any questions or comments, do step up. Just throwing out some more questions to our panel here. So we have the S-Dino spec here. We have the existing Dino spec. If you go out onto the expo floor, there are a lot of Dino Type 2s that are out there. There are Type 3s that are floating around, even though that spec was never completed for all parameters. How does Dino Type 2 fit in with the S-Dino? Andy, you want to help us with that one?
Sure, yeah. So Corey talked about those so-called Zone 2 KOZs on the bottom side of the HPMs, and some of the lessons learned we went through with actual implementations of DNO Type 2 based HPMs, for example. Unfortunately, that was one of the big changes between a Type 2 DNO and, let's say, the Class A SDNO, was movement of some of those KOZs and actually reduction of the size to get more flexibility for the core elements. And so that can create an incompatibility between a DNO Type 2 and a SDNO Class A. You may get lucky in that you just happen to not have components in that area and it works, but there's certainly no guarantees between those two.
All right, thank you.
I just wanted to add, if you look at the SDNO draft spec, we do have a section in the back that talks about if you have an existing HPM or if you want to design a chassis that can support both, some guidance on how to do that. So.
All right, we have a question from the audience.
Yeah, I think maybe my question is going to be answered on the next one, but I'm not going to be here. But can you just speak a little bit about the peripherals, or, you know, Yosemite has like sidecar concept, and, you know, you're focused on the HPM, so I just wanted to get your vision on like how many devices, what type of devices customers you think will expect, whether it's the GPU acceleration or, and how would you accommodate that mechanically in something like a high-density blade type of system like Yosemite?
All right, thank you. Who wants to handle that one?
I'll take a crack. So the specs are HPM specs. There's no chassis requirements called out in the specs. But as the inputs to these, right, there's lots of considerations from platform providers like Dell and Meta, Microsoft, others in the work group, HPE, right? When we're formulating plans, there's a lot of discussion on what are the use cases, right? Are these like enterprise use cases? Are there cloud? Is there scale out GPU type of platforms? And so we discuss and we share a variety of system implementations, which include exactly what type of I/O devices or what type of chassis environments do you have, you know, sidecar type of environments, or do you have something like Matt was showing on the Meta implementations? And so we try to ensure that a lot of both the mechanical constraints as well as the I/O approaches in the spec enable the variety of use cases that this work group brings to the table and has plans for the future, right? So, we're not going to necessarily see documented recommendations from this work group, but we absolutely have a very wide array of system types and system designs in consideration, and we're trying to make sure that our specifications enable all of those use cases.
Follow-up question, sorry.
Yeah, go ahead.
Yeah, so I'm just very curious about these peripherals, right? I mean, these are obviously high-density blades, and, you know, as you start looking at other use cases, like even just a bunch of flash, you know, how do you account for all the I/O that's needed to really do, you know, front-to-back ratios and sufficient I/O to handle, you know, even just 12 NVMe drives, for example? So how does that work out in terms of I/O? What do you envision there?
Maybe this is a CPU question as the CPU suppliers continue to provide more I/O.
I mean, I guess one way to look at it is there's, you know, the multi-track, right, connector there, right? That's the preferred riser, and those can all be cabled, right? Those are dual-use interconnects. And if you have more lanes available on that CPU, there's an understanding that you're likely going to use some 1026 or 1016 connectors in addition to the multi-tracks to get, you know, everything busted out to cables. So that's still there, that capability is there. Those connectors are not placed in the spec. You have latitude as the HPM designer to place those, but we do have reference XIO connectors that we expect the community would use.
I just want to add real quick, in AMD's booth, you actually show cabling from one of the front connectors to the back of the chassis. So take a look in the booth at that.
All right, unfortunately, that's all the time we have right now. I'd like to thank everyone on the panel. We do have a break in this room from 9:30 to 9:40, so the panelists come down. I'm sure they're more than happy to answer questions one-on-one. Thank you.